conclude this course today. And if you need further discussion on it, let me know, then I can arrange classes in the next week. Probably you need some time for your preparation for your exam, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, actually the thing is that we have our thing that is almost at the end. In our last class, we talked about Laplace transform and its application to electrical system. Then we are going to discuss a bit more about it. Then I will conclude my lecture with an example. How can we apply our Laplace transformation technique to our electromechanical system? Probably you have some idea about it from your control engineering. Okay, let me share the slide. They are not open. I cannot find it actually. Where have it gone? Okay, can you see it now?
Yes, sir.
Probably we have talked about this problem earlier, but okay, no problem. I am repeating it. Then we will be switching to some other issues. So what you have to know that we have three different methods to use Laplace transform in solving our electrical system. One, you can, if your impulse response is available, then you apply your convolution property there to find the responses. Just simple Laplace transformation of your impulse unit impulse response, multiply it with Laplace transformation of your input. This will give you the zero state response in the Laplace transform, then you take the inverse. Our second thing is that if we can derive the input-output relationship in time domain, then you can apply your Laplace transform to the differential equation, then you can easily find the total response of your system, the zero state response and zero input response also. And the third and more widely used technique is you can convert your network into Laplace domain by element-wise transformation that we have illustrated in our earlier classes. Now I will be dealing with another problem. You see that in the network that is given at the top is a time domain form. Okay, the initial values of your inductor current and capacitor voltage are also given, and the polarities of capacitor voltage and direction of current through inductor is very important in representing them in the Laplace domain, because we will be using some sources to represent the initial values. If the directions are not properly indicated there, then your derivation will be wrong. But still, if you have some
Welcome back to
confusion
Control System Lecture.
and after deriving the output, you can also check whether this is formula is correctly derived or not by using initial value theorem. So let us start with, we have to start from your source. Okay, your source is a step with amplitude equal to 4. Its Laplace transform is 1/4 by s. Then your resistance is remain unchanged, and your inductance is replaced by Ls, and the initial current of your inductance will be represented by a current source in parallel with the inductor. And you see that the direction given here is same as the direction we used earlier. This is what the thing we are assuming, that your current is flowing from the indicated direction given in figure 1, but your current is negative actually. So your negative values are given there. So this source -2 divided by S is equivalently equal to the representation of the current, initial current with value equal to -2 ampere through the inductor. In the same way, your capacitance voltage can also be represented by a current source equal to 5 multiplied by capacitor. 5 is the voltage with that polarity across the capacitor. Now, you know from your earlier element-wise transformation technique that we have our two architectures, that either we can use parallel or series. But here in this problem, if we use series architecture, it is a bit simpler to solve the network, because the network is a parallel one. How many nodes are there? How many nodes are there in this network?
2 nodes, sir.
Yes, in this network we have only 2 nodes. Okay, one node
Yes,
is a
sir.
reference node, another node is a voltage V. If we can solve for V, then the rest of the quantities can be solved. So you write your KVL equation at this node. Okay, I will not be showing this thing to you. You have your 3 current sources there, and your current is leaving through this side equal to V by R. Current leaving here I equal to V divided by SL. Current leaving through this branch would be equal to V divided by 1 by SC. Current leaving here is -2S, and current entering the node is 4 by S plus 5C. So you can easily write the equation and solve, insert the value of R, L, and C there, and solve for V. Once your V is available, that V is your Laplace domain voltage. So this is what the value of V. Once this value is available, then you take Laplace inverse. Your Laplace inverse can be taken by factorizing our Laplace function, something like this. Okay, you can easily factorize it into some smaller factors, but without factoring, if we have a quadratic factor as a denominator, you can guess that that quadratic factor in the denominator will give you the time domain function that could be represented either by sine or by cosine. So in this way, you can easily take advantage of this comparison to find the Laplace inverse. You see that our s square plus 8s plus 20, that can be represented as s plus 4 square plus 2 square, isn't it?
Yes, sir.
Yes, sir.
So if we can do that, then this is what your denominator. Then in the numerator, you have your 2 terms there, 5s plus 480. You can easily split it into 2 terms. One is 5s plus 4, another is 230 multiplied by 2. Then by comparison with your standard function in the time domain, what is the Laplace inverse of this term? It is simply equal to 5 e to the power minus 4t cosine 2t, isn't it?
Yes, sir.
Yes, sir.
And for the second case, it will be sine. So this is what your output. Now, if you want to find the current, then what you can do, you can use your time domain technique to find the current, or you can use your Laplace function there. Okay, this current I is current flowing through the inductor, and it is there connected in this way. Okay, so if it is your SL, then what is happening? The current flowing through this inductor will be equal to simply this. Now the question is this is the okay, this is the current, then it is equal to V divided by SL. If it is V by SL, then your AC, you put the value of L, and this is what that factor. Now you see that it is not a quadratic factor. Okay, then what you need to do? Can you use your earlier thing directly here?
No, sir.
Then what you need to do?
Partial fraction.
You have to partial fraction it. Okay, after having this thing partially fractioned, you can again use the comparison technique to find the what we call initial values. Now tell me, is there anything wrong with this calculation? Okay, please check it. Okay, you have to check it whether there is any mistake in this calculation or not.
Yes, sir.
Okay, now we have our another category of problems where you can have some active devices in it. In some cases, when a transistor or BGT or some other devices are there connected in a network, they can be represented by their equivalent network that will contain some dependent sources. So if your network will contain some dependent sources, you can easily understand that those network contain some active element in them. And you can easily handle this. We have handled one of such thing in our earlier lecture. Now, if we have our operational amplifier can also be represented by this type of sources, but in our case, we are assuming that our operational amplifiers are ideal. You know the properties of your ideal operational amplifier. So we can proceed with in the operational ideal case, there will be no any voltage difference between your positive and negative terminals of your operational amplifier. As a result, your negative terminals appears to be a ground. Okay, that's equal virtual ground. So what type of operation is being performed by this operational amplifier circuit? Can you guess?
Sir, integrator.
It is a leaky integrator. Okay, so if this is an integrator, then you can easily obtain the transfer function of this circuit. Okay, either you can directly use formula that you have learned, or you can write your equations, the nodal equations at the node, and you can find the input output relationship. Like your previous technique, what you need to do, you can, this circuit is in the T domain, time domain. Then you convert the network into frequency domain by element-wise transformation. Okay, no voltage is given here, so your voltage can be okay. Now voltage is given there. Your voltage is equal to 3 to the power minus 5t. So in this network, this is Vs. This Vs is equal to what? 3 divided by S plus 5. Now your R remains unchanged. Your R is there. Your capacitor is replaced by 1 by C. You can put the value of R and C is there to write the equations. Okay. Then after having your thing transferred into Laplace domain, then where you can have your Kirchhoff's voltage law to be applied. This is what the point where you can apply your Kirchhoff's current law. A current entering that node will also be going there and going this branch and this branch. Okay, no current is flowing through there because of ideal nature of your operational amplifier. So in this way, if we can write our Kirchhoff's current law at this node, you can easily find that this will be equal to this. Then using this thing, you can find the input-output ratio, and that will be actually sometimes we refer that gain in time domain. So this will be equal to this. Then you can easily take the Laplace inverse. Okay, if someone wants to use this formula, that your V equal to minus Vi multiplied by say Z in the feedback path, ZFS divided by Z in S. Here your ZFS is the parallel combination of these two. This is your ZFS and this is your ZIS. Okay, in this way you can also find the thing. Okay, thank you. Because I have to respond to some calls, some messages continuously coming. BOS by VIS is determined. You can also calculate the impulse response taking this inverse, or if your input is given, you can find the output. Okay, along with this thing, we may have our electrical system that might call magnetic circuit. Magnetic circuit
Sir, we can't hear you, sir.
in electrical second course, electrical circuit 2, did not you learn? If you have no response, then you cannot hear me?
No, sir, your network is unstable.
Can you hear me?
Sir, there is a connection problem, sir.
Can you hear me now?
Yes, sir.
No.
Yes, sir.
Now can you hear me?
Yes, sir.
Yes, sir.
Okay, then do you have experience of using coupled network? Magnetically coupled?
Yes, sir.
Yes,
So
sir.
then you know how to handle it, okay? The similar technology or similar thing can be applied there. Only difference will be a mutual inductance will be occurring between two coils, okay? Your dot convention says that if your current is entering through the dot terminal of a coil, then the voltage appearing in the opposite end will be positive, okay? So in this way, you can write your, okay, take help of your Alexander Sadiku's book, how to write the equations for a coupled network, okay? The Laplace transform can equally be applicable there. So that is what our, what we call, I will be extending this thing further by using whiteboard to illustrate few more problems or techniques. Okay, so far what we have considered only either a step source or what you call some exponential sources or something like this. You may have your sinusoidal sources, you may have your pulse type sources that will not be continuing forever. In such cases, how can we apply Laplace transform there? Actually, the thing is that whenever your net input can be Laplace transformable, then you can readily apply Laplace transformation technique for your system analysis. But if your input cannot be Laplace transformed, then it will not be possible to apply Laplace transform there. But fortunately, in most of our cases, we can generate a general signal with the help of some standard signal. For example, a single curve can be approximated by a small rectangles or some impulses, something like this. In this way, we can apply Laplace transform in almost all of our linear systems. Let us consider that we have a pulse. We have discussed this thing earlier several times, that if we have a pulse, say this pulse is 1 second duration with amplitude equal to 1, say this is a signal xt, and that is applied to an RC network, say R equal to 1 ohm or C equal to 1 farad. And you have to calculate the voltage across your capacitor as your output. Okay, this VO is your output. This is your, say, VI is equal to, say, X, the input. So in order to apply our Laplace transformation technique, what you need to do first, you have to take the Laplace transform of your input. That means we have to find VIS. Can you tell me what is the Laplace transform of VIS? Because you see that your VI can be expressed as 2 unit step. One is UT, another is UT minus 1, isn't it?
Yes, sir.
Then what is VS? Your VS would be equal to 1 divided by S minus, what is the Laplace transform of UT minus 1?
e to the power minus 1 divided by
E to the power minus S divided by S. So this is what your input Laplace transform. Now in the output, if we transfer our network, then our network will be equal to what? Your output will be Vs, R will remain unchanged, then your C will be replaced by 1 by Cs is equal to 1 by S. So this is what your S domain network. Then your VOS is equal to what? Your VOS is simply equal to 1 by S divided by 1 plus 1 by S. This is what your potential divide rule multiplied by VOS, VIS. Then you can consider this then as a transfer function if the ratio of V output and V input is taken. Then if we put our V input there, then your V output S would be equal to 1 divided by S plus 1 into 1 by S minus 1 by S e to the power minus S. And this is equal to what? 1 divided by S plus 1 into S minus 1 divided by S plus 1 into S e to the power minus S. Now we have to take the Laplace inverse of VOS. Equal to what? You see that this factor can be factorized in this way. 1 divided by S minus 1 divided by S plus 1. Can you do that?
Yes, sir.
Yes, sir.
Then what is the Laplace inverse of this term? It is equal to UT minus e to the power minus TUT, isn't it?
Yes, sir.
Okay. Now we have a second term there. That second term contains a main term, something like this, and a delay term is there. This term in your Laplace transform is coming because of time delay or time shift. So your second term will have the Laplace transform simply ut minus 1 plus ut minus 1 minus
e to
e to the power minus t minus 1 u t minus 1. That's it. Is it okay?
Yes, sir.
Yes, sir.
This here, the network is creating disturb. Can you hear me?
Yes, sir, we can hear you.
Yes, sir, we can hear you.
Yes, sir.
So this is your Laplace transform. Okay. Now you have to understand that this equation satisfied the way that we want. Actually, according to our previous learning, that if we have a pulse like something applied to our electrical circuit of this type, then what happens? And your RC equal to 1, then what will happen? Your capacitor is getting charged gradually, going to a value, and then again discharge, isn't it? That means
Yes,
the output of your
sir.
capacitor will be something like this, isn't it? This curve. Now you have to tell
Yes,
me that our output that we obtain is equal to ut minus ut minus 1 minus ut. Somebody has frequently putting camera on. Do not do this. Ut minus 1 minus ut plus e to the power minus t minus 1 ut minus 1. This is what our equation we obtain. You have to, for example, if you plot ut, how ut will look like? Ut is a unit step, isn't it? And if we were e to the power minus tut. So if we plot e to the power minus tut and it is minus, where it will go? This value is 1. This value is minus 1. Then your second term is something like this, isn't it?
Yes.
This curve is what? Minus e to the power minus t ut, isn't it?
Yes, sir.
yes, sir.
Then if we add them together, how it will look like?
So it will
If we
start
add this
from
curve,
the
is
exponential.
it not something like this?
Yes.
If we add them together, it will be something like this, isn't it? Now, we will not be drawing these two curves, okay? In this figure, if we draw this curve, this is what our output. If we add these two terms, first two terms, this is equal to 1. Now we have our 1 there, time. At that time, some other things are happening. What is happening? At that time, you see another pulse is there with negative ut. This must be ut minus 1. Okay, ut minus 1. So we have a curve there, something like this. This is your what? E minus u, t minus 1, isn't it?
Yes, sir.
Sir.
Now at this
Yes,
point, we
sir.
have a curve. Sorry. Now we have a curve at this point with positive value and it starts at t equal to 1. And what is it? Is it not something like this?
Yes, sir.
Is
Sir,
it something
it
like
should be.
this? I
It
don't
should be.
I don't think so. It
It
should
should
be
be
decaying something, okay? So if this is 1, then it is actually, let me use another color, then it will be something like this, isn't it?
Yes, sir.
Yes, sir.
So if we add them, these three curves together, how it will look like? Because you see that in this region, this is negative and this is positive. They will be cancelling each other. At this point, the value is same as this point, okay? So what is happening then? Your curve is something like this. If this is 1, your curve is something like this. Is it okay?
Yes, sir.
Yes, sir.
So this is how your system is working, okay? But if you have your complicated system, doesn't matter, okay? What you need to do, you just obtain the transfer function, multiply it with what? The input transform. That will give you the output transform, take the inverse. Okay, in this way, you can proceed further. Okay, let us extend this problem to example, complicated a bit. Consider that if we give this pulse to the input to our capacitor, then what will happen? In the same way, can you take the Laplace transform of this function?
Yes, sir.
Okay. In what ways we can do?
So we can divide it in 2 ramp.
You can divide it in a portion of ramps, not actually RAM, isn't it? You can divide it in this way. This pulse can be split up into network is creating problem. Can you hear me?
Yes, sir.
Yes, sir.
So your part is this one, and another can be what? Something like this, isn't it? So you can take, if we add them together, that will give you the transfer function. Okay, you can have a look to your Alexander Sadiq's book how to do that. But
দোস্ত A1 এ ওই যে যেটা বলছিলে আমাদের গ্রুপ আব্রাহাম মাহির আর কে কাছে একটু বলতো
এই কি হয়েছে এখানে
চিল্লানো
ক্লাসের সময় কেডা চিল্লায় এরকম করে? Is it okay? If we add these two things in this way, you can have your thing there.
Yes, sir.
Okay. But you know the properties of differential and integral properties of Laplace transform. Can we, for example, differentiate this function like dx by dt? How it will look like?
Sir, pulse.
Is it not something like this?
Yes, sir.
Yes, sir.
Yes, sir.
Then you can take the Laplace transform of this function, then use the integral property to go there. Okay. So you try to solve this problem for this RC network. Okay. This is left to you to be done.
Yes, sir.
Okay, in this way you will see that in your book that I am repeatedly referring Sadiq's book. If you have your new edition with you, then you will find many interesting problems there with this type. Okay, try to get accustomed how to solve them. Now I will be going to another important application of Laplace transform in your electromechanical system. Okay, have you modeled a DC motor or separately excited or self-excited or series type motor in your control engineering?
No, sir.
No.
Sir, we only did
Then,
the basic motor,
nothing?
sir. Only one, the general
AC?
motor.
Sorry, short motor? I cannot follow you. Can you repeat, please?
So we just did the general motor, like externally excited.
General motor means what type of motor? General motor means what?
I mean, externally excited using separate circuit.
That this motor has a particular name. Okay, we cannot call it a general motor. If you have a DC motor, you have some type. Okay, you cannot devise your own motor by your own. Okay, we have already established type of motor configuration. Okay, your DC motor can have basically a series type motor. It can have a separately excited, self-excited shunt type motor, or cumulatively compound or differentially compound or something like this.
Yes, sir.
So if we are considering a separately excited DC motor, what will happen? What is the model of the separately excited DC motor? It will have a field coil. Okay, that field coil can be represented by a field resistance and a field inductance. This is your field resistance R, field inductance LF. We apply a field voltage there, VF. That creates a current IF. That current IF creates flux, and that flux causes your motor to rotate in the presence of an armature voltage. Then this is your field circuit. Your armature circuit is represented by a symbol something like this. That is what your armature. We are separating the resistance of the armature, Ra, and separating the inductance of your armature, Rf, La. Then what will happen? A voltage is applied there. That voltage is armature voltage Va. That will cause a current, armature current Ia. Okay, when your motor will begin to rotate, that motor is coupled with a shaft to a, for example, load. Loads are usually represented by what? A rotational object with inertia constant J and a friction B. Isn't it?
Yes, sir. Yes, sir.
Yes, sir.
And if this shaft is rigid, what do you mean by rigid shaft? That means when the shaft motor is rotating, no deformation will be there in the shaft. As a result, no spring action will be there, because we know that we have our three elements in mechanical, like resistance, inductance, and capacitors. An inertial element J or mass in translatory type, a frictional element B, and a spring element K. Okay, but in the case of rotational object, that spring element is called torsional constant, and frictional constant is B. All these things will consume the electrical energy, but the J will not consume the electrical energy. It will store the electrical energy in terms of rotation, or actually the kinetic energy. Okay, if this is your separately excited DC motor, then how many control strategies are there? You can control the speed of your DC motor by changing the field current. This is called field control strategy. Or you can change control the speed of your DC motor by controlling the armature voltage. That is your armature control strategy. Which strategy is followed where? Do you have any idea? It is supposed to be taught in the second year when you have been introduced to DC machine. Field weakening process is used up to certain point. Then beyond that point, you cannot use your field to raise your speed. You have to use another technique there. Because I cannot teach you everything. If you have some thing with you that you need to know, you explore by your own, okay?
Yes, sir.
Because this is very important. This is the basis of speed control.
Yes, sir.
So your field weakening process is not efficient. The reason is that if you increase your field current to decrease your field current to increase your speed, then that will constantly decrease your torque. If it is torque is decreased, motor cannot, for example, supply proper amount of power to drive the load. And even if you increase your armature current to do that, you cannot go beyond the rating of your armature current. A compromise is always there between your field control and armature control. One side is called constant torque operation, another is called constant power operation. That you have to know. So in this case, if you want to model it, then you have to fix one thing, then try to model. Okay, for simplicity, if we consider, okay, let us write the equation, then we will apply which control strategy we are doing. For example, in the field circuit, what will happen if we write the Kirchhoff's voltage law? Then your VF is equal to RFIF plus LF DIF by dt. So this is a separate excited motor. So this circuit is separate. But how they are connected? They are connected magnetically, because this current IF will be producing a flux. That flux will create something there inside your motor. So this field circuit equation is something like this. Okay, if we neglect any coupling effect between field and armature windings. Okay, here in this case, I want to ask you one question. We have a resistance in the field circuit RF, and we have a resistance in the armature circuit RA. Which resistance is higher and why? Hey, did you perform any experiment in the laboratory regarding speed control of a DC motor? Because we have our sophisticated DC machines in the laboratory. এরকম পারফরমেন্স হলে তো সার্টিফিকেট পাবা না, আটকায় দিব। এগুলোকে সার্টিফিকেট দিয়ে 2 দিন পরে কোনো কাজ করবে না, জানবে না, শুধু কি ইউনিভার্সিটির নাম দিয়ে চলে নাকি কিছু না জানলে? দুর্নাম হয়ে যাবে তো, তোমার ইউনিভার্সিটির দুর্নাম হবে, তোমাকে যারা পড়াইতেছে দে উইল অলসো সাফার ফ্রম ডিফেসিং। Then in the armature circuit, what will happen? In the armature circuit, if we write the Kirchhoff's voltage law, VA is equal to RA IA plus LA DIA by DT. Is this equation complete?
No, sir.
Then what additional terms are needed?
Terms due to the inertial.
ফিজিক্যালি ক্লাস নিলে তো তোমার ক্লাস থেকে আমি বাইর করেই দিতাম, কিন্তু এখানে তো আর পাইতেছি না ইনার্শিয়াল টার্ম। When a flux is there, your motor is rotating, then what will happen? Another EMF will be created there, back EMF. Have you heard the name back EMF?
Yes, sir.
If your back EMF is not available, can you run a motor?
No.
No, sir.
Because in your armature winding, the resistance, that was my first question, that what is the relative magnitude of RF and RA? But you are remaining silent. But your common sense can tell you that what could be the relative values of RA and RF. Because this RA we do not want actually. This is the winding resistance of your armature that will lose power. But this resistance is needed to control the current. So this resistance should have a value that is very minimum. In the, for example, order of ohm or milliohm, or in larger machines even lesser than this. Then if we write the equation in this way, it is a DC motor. In the that only the resistance that is controlling armature current. Then thousands of amperes of armature current will be flowing through your armature, and in the wink of an eye, your armature will be getting burned. For this reason, when we are starting at the starting point, we need a device to start the motor that is called a starter. Have you seen it in your laboratory? তোমার পড়াশোনার কোনো ভ্যালু নাই, যে পয়সা খরচ করে বাপের এত টাকা খরচ করে পড়তেছ, জাস্ট দ্য আউটপুট ইজ কমপ্লিটলি জিরো। So your armature voltage, armature circuit equation is very important for operating your motor. I taught my student this electrical machine about 30 years ago, and still they are doing in many for example industries. Okay, and when I meet them, they still can remember what I have taught them. But unfortunately, you guys are not that, for example, the thing that you can remember, rather than, for example, what we call humiliating the people. So this is what your equation. And we know that this EMF is a generator action in a motor. And that EMF magnitude depends on how many windings are there, how many flux it is cutting, and what is the speed of your motor. As a result, it will always be the function of field current and speed. So this will be equal to RA into IA plus LA DIA by DT plus a constant K with a field current IF and your speed omega, if this is rotating in omega. If we are in SI unit, then omega radian per sec current ampere. In this way, you can easily find what will be the unit of your K. When this current IA is available in your armature, then what will happen? That current IA with current IF with a constant Km, that will create a torque. And that torque is the torque that will cause, for example, your machine to rotate. and that torque will be utilized in three different components. One, to overcome the inertia of your J. Another part will be utilized to overcome or lost in your friction. And the third component can be there stored in your spring like something. If your shaft is rigid, then that term is not there. So generally we can write it J, rate of change of your, this is our angular acceleration, plus B into omega. This is what that equation. You can easily see that you have your equation there. One, VF is equal to RF plus LF into DIF by dt. What I have seen there, okay, recently or few months ago, I examined some MSc engineering thesis. I will not mention the name of the supervisor or anybody. What they have done, they simply copied this thing from the internet and reproduced it in the thesis book. If it were in the United States or even in any private universities doing the same thing, probably the student of the ship of that teacher, as well as the supervisor, were probably driven out from the university. But in this case, nobody is caring about it. Only Ruhul Amin is shouting. So be careful about that, okay? About copying. That's why I hate copying, okay? So they are simply copying. A second year student knows it, but a master's student copying. So with this thing, what you can do, you have your equation 1, you have your equation 2, you have your equation 2. You simply simultaneously solve them to find your speed. As simple as this. But if you want to go to Laplace transform, your Laplace transform can also help you to do that. How can you take the Laplace? You take the Laplace transform of a field circuit. It will be equal to VFS is equal to RF IFS plus LFS IFS. You can easily solve for IFS. Once your IFS is available, then you can find your EBS. Your EBS would be equal to K, say KB, the EMF constant, into IFS, into say omega S. We do not know yet how omega S will be coming. Now our armature circuit VS is equal to RAIAS plus LAS IAS plus EBS. That EBS already know, you have not. Then your mechanical equation is torque S is equal to Km IFS multiplied by IAS is equal to JS omega S plus B omega S. This is what your three equations, algebraic equations. Now, you can simultaneously solve them to find your speed omega S. But in many of our cases, if we want to use armature controlled machines only, then field excitation is fixed. In this case, what will happen? These two will be coming into the form of another constant. If they are coming into the form of another constant, then what will happen? Your back EMF will be a multiplication K with omega S. And your torque will also be equal to a constant K with IAS. Here in this case, if your units are SI, the unit of the K of both K will be same. But if your units are not SI, then back EMF K and torque K will be different. That you have to know why they are different. So this is your back EMF. Now, if we set this thing without considering that we have our
Hello, sir. Hello.
Sir, we can't hear you.
Oh, my connection was lost. So what you can do, again I am rewriting it, that you have used some, again somebody is putting camera on and making my window cluttered with their figures. That's what you can do. Use summary there. You apply an armature voltage with transform VAS. Then you have a feedback loop there and a constant K is there. This input should be the speed omega BS. Then this must be negative, this is positive. Then you will have a difference there, VS minus EBS. That is what the important thing controlling the current of your motor. Then we divide it by RA plus LAS. This is what your current IAS. Then you multiply your current IAS with a torque constant. This is what your torque TS. Then you apply this torque to a motor load. That load is again JS B. Then your output will be equal to omega S. Take this output as a feedback in this way. So this is what an armature controlled separately excited DC motor. Okay, if everything is given to you, you can easily calculate the thing. Okay, lots of examples are there in your book, or you can find the value. Okay, or you can pick a problem from your text that you have used in your second year when energy conversion 1. Then you can easily find this thing. Okay, so this is actually an open loop type. But you can also example that say omega RS. Then you can take this feedback there to compare the real speed with your omega S. This is plus, this is minus. Then an error signal will be there, that error in speed. Reference S minus omega S. Then you place a controller there, armature voltage there, and that speed will be remaining constant.
Sir, can
Okay,
you,
what type of controller you have studied so far? Sorry?
sir, can you repeat this part? Your voice
Hello, hello.
bothered.
Yes, sir. Can you
What
repeat,
part of
please?
what? Sorry?
Sir, your voice wasn't hearable
part?
for around 2 or 3 minutes.
Yes, sir.
At what part? Which part you,
Sir,
my voice was not hearable?
Sir, a little after you started drawing this figure.
Okay, when I am, can you look into this figure? Can you see this figure?
Yes, sir.
Yes, sir.
Okay, in drawing
Yes, sir,
this
we can.
figure, if you in drawing this figure, what was the problem that you did not understand? That I can repeat.
Sir, in the last part, what did you say? We did not hear. When you were drawing the left
In the
part
last
of
part,
the,
I did okay.
Sir, upper left portion, sir.
This portion.
yes, sir.
Okay, this portion.
Yes, sir.
This portion. Okay, but you understand the rest of the thing?
Yes, sir.
Almost, sir.
Okay, start with the equation, then it will be easy for you to understand. Okay, you see that your IAS equal to what? It would be equal to VAS minus EBS divided by RA plus LAS. Is it okay?
Yes, sir.
Yes, sir.
Fine. Now your speed TS, torque TS would be equal to JS omega s plus b omega s. Is it okay?
Yes, sir.
Fine. If this is your case, you see that in this equation, EB is equal to what? Your EB is equal to K into omega S. That means this omega is coming there. So what you can do, you can set a block diagram, something like this, okay? You are putting an input there. That input is your VS. You are taking some EBS from some other place, EBS. And you are subtracting it with EA, okay? Then this output of this summer will be equal to VAS minus EBS. Is it okay?
Yes, sir.
Yes, sir.
Then you divide this factor by 1 divided by RA plus LAS. Is it okay?
Yes, sir.
Then what is the output? This output would be equal to IAS. Is it okay?
Yes, sir.
Then you multiply this because your torque is equal to K into IAS. Then you multiply with your torque constant K. That will give you torque S. Then you divide this torque by 1 divided by JS plus omega S.
So you disconnected again.
B, JS plus B. Then output will be what? Your speed omega S, isn't it?
Yes, sir.
Then you
Sir, your voice is distorted. We can't hear you, sir.
okay? Work is awfully bad. I don't know. Sorry. If my okay, is that clear now?
Yes, sir.
Okay. Then I was saying that this is an open loop type of speed control. Okay. If we make it an automatic speed control loop, that we will set a reference and automatically that reference will be maintained. Then conceptually, what you can do? You can set another block there, a comparison of your speed. Okay, set a set speed there. That speed is reference speed. Okay, omega s. Then what you can do? You can take a feedback loop there to put there. Okay, this is your minus. This is your plus. Then what will be the output of this summer? The difference between your reference speed to your speed, isn't it?
Yes, sir.
Yes, sir.
That error signal, this is called error. That error signal key, and that controller will generate an output, for example, VS. This is a very simple and intuitive type speed control system. We need much more sophisticated issues in practice. Now, my question is, do you have any idea that what type of controller is generally used there? Or do you have any experience of studying controller in your control engineering course? Because the name of the control engineering course probably originates from the designing of controllers.
So we have used PID controllers. We have learned to use PID.
You have learned PID controllers. When?
Yes, sir.
In this course, control engineering course, or in another course?
So control engineering.
Conversation.
In control engineering, you just directly have gone to PID.
No, sir. PI and PID we use.
Then you have to say that we control PI and D, not PID. Okay? Either you can use a proportionate controller, or you can use a differentiation controller, or you can use an integral type controller. Okay? Now tell me which of this controller has what effect in your performance? Why we need all these three, or we can use only one, or we can use other. Okay, this is your task actually for your future exploration. So that's it from my part in this lecture. Okay, we'll have our questions similar to our mid-exam. 4 questions will be there. You have to answer all 4. We will take best 3. But I have something to say this time, that I have considered many of your careless mistakes, many of your careless behavior earlier. but I will not tolerate any careless behavior anymore. Be careful about that. The thing is that
Yes, sir.
when I instruct you to follow that, you have to put your file name in a way so that it could be easily retrievable for your teacher. But you are writing your, although most of you are doing that thing good, but few of you, they are careless, so they are putting their thing in their own way. This time, if I found anything that will not comply with my instruction, I will simply reject those scripts. Be careful about that. Second thing is, some of you are using over, for example, what we call size paper, or the paper that actually not need. You see that it is a concern of storage and data. You have to keep your everything there. But some of you are doing, for example, writing something so big letters, okay, only 3 or 4 lines in a page. Answer needs barely 1 page, but you are making 3 or 4 pages. And that is also another problem for your teacher to evaluate those things. So that this time you have to be careful about this, okay? Third thing is that some of you is still adopting some unfair means. Okay, sometimes although the data is different, but still you want to know something from somewhere and putting the results something there. If I found something there, okay, without following any step, the results are there, those scripts will not be evaluated. Okay, you cannot expect, for example, everything what you have enjoyed in the case of your physical learning. As we are distant, no matter how many camera we set, but still, if you want to cheat, you can cheat. Unless your ethical standard is not raised and you do not understand the consequence of cheating, the cheating will be there. So be careful about that. Do not overburden us, please.
Sir, will there be class next week?
Okay, it is up to you. If you want to class to be done in the next week, I can do that. Do you want class, further class?
Sir, we'll decide and we'll let you know.
Okay, if you decide, then let me know it. But formally, I am finishing. I know that you need some time for your practice. Okay, try to practice. If you feel any further discussion to be needed, then let me know it. Okay.
Yes, sir.
I will try to arrange it. Okay, roll number 1, section 1.
Yes, sir.